Okay, chemistry, a help video for gas law problems, combined gas law problems especially. So let's do this problem. We have a sample of sulfur dioxide. It occupies a volume of 652 milliliters at 40 degrees Celsius and 720 millimeters of mercury. You need to be able to identify which of those units are volume, which temperature, and which pressure. Milliliters is volume, degrees Celsius is temperature, and millimeters of mercury is pressure. And the chapter explains all that if you need to review. What volume will the sulfur dioxide occupy at standard temperature and pressure? The first thing to understand is that this problem is giving us some information we don't need. All gases observe, at this level at least, we're gonna play like all gases observe the combined gas law. And the combined gas law is really useful in like virtually all circumstances you're going to deal with in life. It's one of the best, most practically useful things in science, and so I really want you to get it out. You could just say a sample of any gas. Now we're given a starting volume, a starting temperature, and a starting pressure. And then a change occurs. That change is described in the second sentence. What volume will the sulfur dioxide occupy at standard temperature and pressure, STP? Well, what is that? You need to know, I highly recommend you put it on your note card or squirrel it away in your memory, that STP is standard temperature and pressure, and it is defined to be 0 degrees Celsius and 1 atmosphere of pressure. Notice I'm giving that as an atmosphere. We're going to need to convert. What do we have? We have a gas, so that means it follows the combined gas law. We have a volume that we start with, a temperature that we start with, and a pressure that we start with. In other words, we have our P1, our V1, and our T1 given to us. What else do we have? What volume will the sulfur dioxide occupy at STP? A standard temperature and pressure. So there's a change, or at least a new temperature and pressure. We have our T2 and our P2 given to us. So that's all that we have. We have our equation. We know what STP is, and we have these values for our equation. I want you to notice on these values, I converted. So pressure 1 was given to us in millimeters of mercury. I went ahead and converted our pressure 2, our 1 atmosphere, to millimeters of mercury. 760 millimeters of mercury is 1 atmosphere. You just need to know that, be able to do the unit conversion. Our volume 1 is given to us in milliliters. That means our volume 2 is going to come out in milliliters, but we don't know it. That's what we're trying to solve for. I went ahead and changed both of our temperatures to Kelvin. That's just for convenience sake. So both temperatures are being represented in Kelvin. What do we have? We have all this stuff. What do we need? Some of you guys need to work on your problem solving and problem reading. What is the problem asking us for? The volume of sulfur dioxide. What will the volume be at standard temperature and pressure? Because you know it's asking you for a volume thing, your answer needs to be in milliliters or some other unit of measurement for volume, but milliliters is kind of convenient because that's what the problem gives us to start with, right? So we're going to plug in our different values into the equation that we have and work the algebra. I think that you guys know how to do the algebra. If you don't, talk to me and we can work algebra together. But I'm hoping that you already have that skill set. It's kind of, this class is beyond basic algebra. So you should be able to do this kind of algebra, plug in your values, and then work through. Eventually you are going to get a volume 2 of 538.8. And then if you look at the significant digits that the problem gives us to start with, the most we can give for an answer is 2 because we only have 2 going in. So our answer is going to be 540 milliliters. 540 milliliters. So that is a quick example on doing a combined gas law problem. Start with what you have, write down your equation, write down all the values that you know, and then solve for what you need. Pretty straightforward. Let's talk about a different kind of problem, more of a conceptual problem you're going to see on that homework assignment. We'll do one together, or we'll do number 3 together. If you want to cool a gas, which gas law could you use, and how would you do it? Well, start by what you have and find out what you need. Which gas law could you use, and how could you do it? We've learned several gas laws. You need a gas law that has to do with temperature, because cooling is just a change in temperature. You need a gas law that has to do with temperature. Well, look through your book, or maybe on your note card, or go through the gas laws in your mind. Is there a gas law that employs temperature? Here's one. Pressure 1 over temperature 1 equals pressure 2 over temperature 2. What this means is that there's a direct relationship between pressure and temperature. As pressure goes up or down, temperature goes up or down. Now, with this law in mind, okay, I know I need to cool gas, so I went looking through my book or my note card or my memory at all my gas laws. Which gas laws touch temperature? Well, this one does. So we're searching through looking for gas laws that have to do with temperature. And you might find more than one, but you will find this one. This one, Gay-Lussac's law, tells us that pressure 1 over temperature 1 equals pressure 2 over temperature 2. In other words, there's a direct relationship between pressure and temperature. As pressure goes up, temperature goes up. And that implies that as pressure goes down, temperature might go down for us. We're looking for a gas law to do with cooling or temperature, and here's one of those. So could we use this principle, to cool a volume of gas? Let's see. Let's do some math here. Let's just play with numbers. Let's say that I have a pressure 1 of 100 atm, and I have a temperature 1 of 500 Kelvin. Okay? Now I'm going to change the pressure. I'm going to dramatically decrease the pressure to 5 atm. What is that going to do to my temperature? What's my new temperature going to be? Well, I'll do some algebra for you guys. 100 over 500 is 0.2. So 0.2 equals 5 over T2. I'm going to call it T question mark because we're trying to find out what it is. We can rewrite this. That's just confusing. We can rewrite this as T question mark times 0.2 equals 5. And then we divide both sides by 0.2. 5 over 0.2 gives us 25. So our T question mark, T2, is 25. 25 what? 25 degrees Kelvin. It looks like when we dramatically decrease the pressure, it dramatically decreased the temperature. And that's consistent with what Gay-Lussac's law tells us, that pressure and temperature are directly related. So if we wanted to cool a gas, we would use this law. And what would we do? I'm just going to call it GL law. Using the GL law, decrease the pressure, which we can say is P2. And this will require the temperature, T2, to decrease. Temperature and pressure are directly related. All right, there you go. Really not too complicated. How did we do this? We started by carefully reading the problem. I want to cool the gas. Which gas law could I use and how would I do it? So I want to cool a gas. I have gas laws and I need to cool a gas. One of my gas laws talks about changes in temperature. So look through your book, look through your memory, look through your note card, find a gas law like Gay-Lussac's law that gives us a change in temperature. And then how could you manipulate the math to do a change in temperature? Play with the math a little bit. Plug in easy values like 100 and 505. Don't make it complicated on yourself to test it out. And then explain. Use complete sentences. They don't need to be long. They don't need to be wordy, but be clear and concise.